How you doing? My name is Jonathan Cheatham, and this is my MA 383 Foundations of Mathematics WPR2 Intro. So we're introducing proofs and how it's different from other math courses we've taken. Other math courses simply look for a step-by-step process looking for an answer, while Foundations focuses on the proofs and being able to mathematically understand the reasoning and theorems behind all the rest of math. We have to take general concepts and be able to break them down into their most minute details and explain them to a reader who may or may not be familiar with mathematics. A specific example is breaking down simple multiplication problems into definitions of even and odd numbers, or for the following proof, dealing with sets, I had to specifically redefine a law that we had learned in the first 2 weeks of classes in order to use it to prove the statement that I was assigned. It's very difficult for most people to comprehend because you're using well-known knowledge that you feel as though is common knowledge to everyone, and you have to re-explain this in a simpler fashion in order to clarify everything and leave no gaps in a reader's understanding. Many things can be taken for granted, but it's definitely given me appreciation for a step-by-step process and ensuring that I have explained everything in the most minute and simplified details that I can. Next, we will walk through the steps of the proof guide. We want to prove that f of a intersect b union c is equal to f of a intersect b union f of a intersect c. First, we state it as an if-then statement. If x is in f of a intersect b union c, then x is in f of a intersect b union f of a intersect c. Next, we write down our know. It's the first part of this if-then statement, so we know that x is in f of a intersect b union c. Next, we write down our show, the second half of the if-then statement. So x is in f of a intersect b union f of a intersect c. Step 4 is to expand our know. So by the definition of image, we know that there is a y in the set y such that f of x equals y for x in f of a intersect b union c. The final step is to expand our show. So this means that there is a y in set y such that f of z equals y for z in a intersect b, or there's a y in set y such that f of u equals y for a u in a intersect c. The final step of the proof guide is to do the complete proof. Before we begin our proof, we need to define what I'm calling Cheat's lemma, and that is to prove that a intersect b union c is equal to a intersect b union a intersect c. Because of the statement, we must prove two statements. 1, a intersect b union c is a subset of a intersect b union a intersect c, and 2, a intersect b union a intersect c is a subset of a intersect b union c. So for statement 1, if x is in a intersect b union c, then x is in a intersect b union a intersect c. So we let x be in a intersect b union c. This means that x is in a and x is in b or c by the definition of union intersection. If x is in b, then x is in a intersect b. Thus x is in a intersect b union a intersect c. If x is in c, then x is in a intersect c. Thus x is in a intersect b union a intersect c. Therefore we approve the statement a intersect b union c is a subset of a intersect b union a intersect c. So now we prove statement 2. If x is in a intersect b union a intersect c, then x is in a intersect b union c. So we let x be in a intersect b union a intersect c. This means that x is in a and b, or x is in a and c by definition. If x is in a and b, then x is in a and x is in b union c. Thus x is in a intersect b union c. If x is in a and c, then x is in a and x is in b union c. Thus x is in a intersect b union c. So we have now proven that a intersect B union A intersect C is a subset of A intersect B union C. By using statements 1 and 2, we have proven the statement A intersect B union C is equal to A intersect B union A intersect C by the definition of equality. We must prove that f of A intersect B union C is equal to f of A intersect B union f of A intersect C. This means we must show two statements. F of A intersect B union C is a subset of f of A intersect B union f of A intersect C, and f of A intersect B union f of A intersect C is a subset of f of A intersect B union C. First, we prove the first statement. We want to show that if y is in f of A intersect C union B, then y is in f of A intersect B union A intersect C. First, we let y be in f of A intersect B union C. By the definition of image, this means there exists some y in the set such that f of x equals y for an x in A intersect B union C. By Cheat's lemma that we proved earlier, if x is in A intersect B union C, then x is in A intersect B union A intersect C. If x is in A intersect B, then y is equal to f of x for y in f of A intersect B. Thus y is in f of A intersect B union f of A intersect C. If x is in A intersect C, then y is equal to f of x for y in f of A intersect C. Thus y is in f of A intersect B union f of A intersect C. We have now proven statement 1. Statement 2. If y is in f of A intersect B union f of A intersect C, then y is in f of A intersect B union C. Let y be in f of A intersect B union f of A intersect C. This means there exists some y in the set such that f of x equals y for x in A intersect B, or f of x equals y for x in A intersect C. By Cheat's lemma, if x is in A intersect B union A intersect C, then x is in A intersect B union C. If x is in A intersect B union C, then y equals f of x for some y in f of A intersect B union C. We have now proven statement 2. By using statements 1 and 2, we have shown that f of A intersect B union C is equal to f of A intersect B union f of A intersect C by the definition of equality.